Covalent bonding. So if the difference in Z effective is low between the two atoms, the atoms will have to share electrons to attain a stable electron configuration. So now the shared electrons are attracted to two nuclei. And remember that the electrons are negatively charged, nuclei positively charged, so you have a force attractive that is now between them. And in fact, we call that a localized bond, and it's localized because there is that sweet spot between the two nuclei that the electrons want to be. If the electrons are way over here, the radius isn't small enough, the distance between the electrons isn't small enough for the force attractive to increase, because remember that it's an exponentially large factor in which, as the radius, the distance between the charges decreases, the force attractive increases. So because the shared electrons are now between two nuclei, you increase stability. If the two atoms are nonmetals, that forms a covalent bond. We will get to metallic bonds later. So Lewis structures with covalent bonds, we show the valence electrons. And again, I use dots and X's so that it's easier to see at first where the electrons came from. So I have carbon, and carbon has 4 valence electrons. Hydrogen each has 1 valence electrons, and if I combine it with 4 hydrogens, which I know occurs, I can create the compound CH4. And the way that we express this is that you have carbon with its 4 valence electrons now sharing the electrons that hydrogen brings in. So they're both sharing them. Each of them can count them as their own valence electrons. So now if carbon looks around itself, it sees that it has 8 valence electrons. It has a stable electron configuration. Even though it's counting some of hydrogens as its own, it doesn't matter. Hydrogen also can look around itself and see that it has attained a stable electron configuration of 2 valence electrons. So each of them has achieved a stable electron configuration. And remember that that's the #1 driving force. Anytime you have any sort of interaction, the reason why you have that interaction is to attain stability. And when we're talking about stability, that stability, when we're talking about bonding, comes from attaining a stable electron configuration, first and foremost. So we can either represent the covalent bond, the shared pair of electrons, as dots or X's, or we can use the line configuration. And a line represents a pair of electrons that are shared between two atoms. And they radiate outward, so these are all radiating outward at the 12, 3, 6, and 9 o'clock position. So again, carbon is happy because it's achieved a stable electron configuration, and so is hydrogen. Another way to look at it is that because carbon has 4 unpaired electrons, it can form up to 4 covalent bonds. Hydrogen can form only 1 covalent bond because it can only attain the 1s2 electron configuration in order to achieve a stable electron configuration. So if you think about it in terms of that, it makes it easier to figure out what the structures might be. So let's look at a compound in which I have carbons and hydrogens, or nitrogen. Oftentimes what we do is that we put the element that can form the most bonds in the middle because they're the ones that can branch out. So if I have carbon, I have nitrogen, and I know that carbon can form 4 bonds. How do I know that? Because carbon has 4 unpaired electrons, and so it can form bonds with another atom. It's available to share. Nitrogen, on the other hand, can only form 3 bonds, usually. And the reason for that is if you look at its Lewis structure, nitrogen has 1 lone pair. Because it is a lone pair, it is already paired up. It is not able to share a pair of electrons. So really the only set of unpaired electrons that it has are these. So nitrogen can form 3 bonds. And so by drawing the Lewis structure of the atom, you get a sense of how many unpaired electrons are available for bonding. So let's look at different examples. So I have C2H6. I know that C2H6 exists. I put the carbons in the middle. Each carbon can form 4 bonds. Each hydrogen can only form 1 bond. And the easiest configuration for this is to have the carbons in the middle with the hydrogens on the side. Now, another way of depicting this oftentimes is that if there are hydrogens around it, we will just show the carbons and assume that the hydrogens are around that. We will get to that, but just wanted to introduce that. Let's look at other C2H compounds. So we know that C2H4 also exists. So the question is, how does that happen? How do we know that C2H4 exists? Because we have purified it, and we know that it's a pure substance. And when we do the stoichiometry of it, it's carbon, the formula is basically C plus 2H2 yields C2H4. And so that's how I know that that compound exists. Nothing is left over. There's no limiting reactants. It's pure substance. So how do we know that it exists? Well, we think that there's a double bond. We know that there's a double bond. So each carbon, again, count up the bonds. Each carbon has 4 bonds around it. Each hydrogen has 1 bond. And so by forming the double bond, meaning that each carbon is sharing 2 pairs of electrons, you can have this conformation, the Lewis structure. Maybe like, but how does that happen? Well, if I draw the Lewis structure again with just the dots and the X's, and I'm adding the hydrogens on, I have a bond here, a single bond here, here, and here, and I have across a single bond 2 lone electrons that are unbonded. Each hydrogen is happy, but the carbons aren't. There are 2 lone, or what I call dangling electrons on either side of the bond, and as a result, what's going to happen is that these electrons will then form between these 2 nuclei and form a double bond. Maybe like, but that feels like it's cheating. It isn't cheating because remember that the first and foremost important thing is to attain a stable electron configuration. And if it needs to do so by compromising, and in this case forming a double bond, it will do so. So you may ask yourself, but is that stable? And the question is, yes, it is stable because each atom has a stable electron configuration and those electrons are between 2 nuclei. But it's not as stable as single bonds because of the electron density, right? So instead of having 1 pair of electrons between the 2 carbons nuclei, I have 2, and electrons are both negatively charged, and so what's going to happen is that the force repulsive is going to be higher in a double bond than in a single bond, so its stability is lower. So it's not that it wants to form a double bond. It forms a double bond out of a compromise because attaining a stable electron configuration is the most important. So then the next logical answer is, what about triple bonds? Are triple bonds possible? Absolutely. But they're only possible between carbon and carbon or carbon and nitrogen, and that's because of the number of bonds that you need to form. So you have this and this structure, and you can have longer carbon chains with triple and double bonds between them. But here's where you have this, and then this is the lone pair of nitrogen. So again, each carbon has 4 pairs of electrons, each hydrogen has 1, each carbon has 4, the nitrogen has 3. So if I'm looking at stability, single bonds are always going to have a greater stability than double bonds, which will have a greater stability than triple bonds. And again, it's because I have more electrons in a smaller area. Excuse me. And so the electron density is really increasing. Force repulsive increases as well. So even though force attractive has increased because the electrons are between 2 positively charged nuclei, as I add more bonds between them, the electron density increases, so force repulsive increases. So if we talk about stability, remember that things that are less stable react more readily. Things that have triple bonds are more reactive than things that have double bonds or things that have single bonds. And likewise, if I have a very long molecule with lots of double, single, and triple bonds, the triple bonds will react earlier than the double bonds and the single bonds. And we can take advantage of that and create molecules by reacting things, knowing that if we create a molecule with a triple bond first and then react it, it will react at that triple bond specifically before it reacts at a double or a single bond.